a gentle invitation to discovery. Welcome to Night Chemistry, your refuge in the quiet hours. Close your eyes and take a deep breath, letting the air settle in your lungs like a warm blanket around your heart. Tonight, we journey back to the 17th century, where a young man named Robert Boyle stands at the crossroads of alchemy and modern science. Imagine candlelight flickering against stone walls, illuminating ancient manuscripts and glass vessels filled with curious liquids. A hush hangs in the air, as if the world itself waits for a question to be asked, a question that might unlock the secrets of breath and the nature of the universe. Robert Boyle was born into privilege but chose the path of curiosity over comfort. From the grand halls of Lismore Castle to the laboratories of Oxford, he chased knowledge with a quiet tenacity. His experiments with air, pressure, and invisible forces laid the foundation for a new kind of science, one built on observation, doubt, and a steadfast devotion to truth. As you listen, allow your mind to wander the corridors of his world. Shadowy libraries lined with dog-eared books, gardens where glass tubes catch the morning dew, and laboratories where water rises and falls in perfect rhythm to the pull of Boyle's careful hands. Every sound, every scent, every flicker of flame holds a piece of the mystery he sought to unravel. Breathe in, and feel the weight of centuries pressing gently on your chest. Breathe out and let that weight dissolve like mist. Tonight, you walk beside a man who saw air not just as emptiness, but as a vessel of hidden wonders. A man who taught us to question, to measure, and to trust the quiet language of experiment. Settle in and let the story begin. Lismore Castle, the dawn of inquiry. The night air settles over the thick walls of Lismore Castle, its stones cooled by the mist that rolls in from the Blackwater River. Within those walls, a boy named Robert Boyle lies awake, his mind restless. The tapestries that hang from the chamber walls seem to shift in the candlelight, forming patterns that he strains to interpret, signs of secrets yet to be revealed. From his earliest days, Robert was surrounded by books. His father, the Earl of Cork, amassed a library filled with ancient alchemical texts and the writings of natural philosophers. To young Boyle, these pages were more than just ink on parchment. They were keys to unlocking the hidden mechanisms of the world. He devoured them by firelight, his imagination igniting with each new discovery. Outside his window, the night is alive with the sounds of the Irish countryside. A barn owl calls from a nearby oak, its cry carrying across the darkened lawns. The river sighs as it winds through the valley, a steady breath beneath the hush of night. Boyle listens, his own breath matching the rhythm of water against stone. He wonders what secrets the air itself might hold, what invisible currents might shape life and death, wind and flame. By day, he walks the castle grounds, peering into gardens where dew clings to each leaf like a question mark. He observes the delicate dance of insects in the morning sun, the way frost blooms on window panes, the heavy silence before a storm. Everything seems to speak to him of mysteries waiting to be solved, if only he can learn their language. In the castle's lower chambers, Boyle finds his first laboratory, a makeshift collection of glass vessels, iron tongs, and aged manuscripts. There, among the shadows and echoes, he begins his earliest experiments. Heating substances to observe their transformations, mixing powders to test their reactions, watching for the subtle changes that hint at deeper truths. Each spark of flame, each swirl of vapor, is a message from the unseen world, a whisper that the air is not empty but alive with secrets. Late at night, Boyle writes his thoughts in a worn leather journal, its pages crowded with sketches and notes. He records each observation with the precision of a young mind hungry for knowledge, determined to capture every fleeting glimpse of the hidden order he senses all around him. As the castle sleeps, the boy with candlelit eyes continues his quiet explorations. Every breath he draws carries the scent of discovery, and every exhale leaves behind a question. Wrapped in the hush of Lismore's ancient walls, Robert Boyle takes his first steps toward a destiny that will change the way the world understands the air we breathe. The Grand Tour. Seeking knowledge across Europe. Dawn breaks over the cobbled streets of Geneva, its towers casting long shadows across the river. A young Robert Boyle, now a teenager, steps from the warmth of his lodgings into the cool morning air. He has left the familiar comfort of Ireland behind, seeking wisdom in the cities that gave birth to the modern mind. His journey began in Italy, where the grandeur of Florence and the bustle of Rome stirred his curiosity. Amid frescoed halls and candlelit chambers, Boyle listened to scholars debate the structure of the universe, the movements of the stars, and the very nature of matter. He marveled at the instruments of science: glass spheres, brass compasses, strange powders labeled in Latin, and wondered how each might reveal the hidden laws of the world. In Florence, the name Galileo still hung in the air like a challenge. Though the great astronomer had passed, his ideas lived on, whispered in hushed voices among students and professors. Boyle studied his writings by lamplight, tracing the paths of planets in the margins of his travel journal. He dreamed of experiments that might test these theories, of capturing the secrets of the heavens in his own hands. Through Switzerland and into France he wandered, collecting questions like pebbles along a stream. Every village market offered new sights: herbs sold as medicines, curiosities from distant lands, machines that promised to weigh the very air. Boyle watched, listened, and took notes, his mind a sponge for every detail. In Paris, he found himself among philosophers and mathematicians, their salons filled with laughter and the scent of ink. They debated the nature of reality over cups of spiced wine, arguing whether the universe was made of indivisible atoms or continuous ether. Boyle listened carefully, drawn to the idea that the world could be measured, that air and fire and water were not mystical elements but things to be understood. At night, in quiet inns and bustling taverns, he read by candlelight, his breath clouding the window as he traced the shapes of letters with a calloused finger. Each book he carried became a friend on the journey, guiding him through the winding roads of thought and inspiring new questions with every page. These travels, through cities and across mountains, through libraries and marketplaces, widened Boyle's view of the world. They taught him that knowledge was not confined to any one land or tongue, but rather lived in the curious minds of those who dared to ask. And so, with each mile, he gathered the tools he would need for the experiments that would define his life, a collection of ideas, observations, and quiet certainties that air itself held the key to nature's deepest secrets. Oxford, the birth of a new science. Robert Boyle stepped off the carriage onto Oxford's uneven cobblestones with a mixture of excitement and resolve. The city's ancient spires and collegiate cloisters loomed above him, each stone whispering centuries of scholarly pursuit. He inhaled the crisp morning air, laden with the scent of dew-damp grass and wood smoke, knowing that here at last he would build a laboratory worthy of his ambitions. Securing rooms in one of the lesser-known colleges, Boyle set about transforming a cold, narrow chamber into a workshop of glass and fire. He scavenged discarded parchment for notebooks, borrowed extra glassware from sympathetic tutors, and commissioned brasswork from local artisans. Every detail mattered. Each glass tube had to be perfectly straight, each joint sealed without flaw, every balance calibrated to the finest grain. Within weeks, Boyle's laboratory took shape. Shelves groaned under rows of retorts and alembics, their curved necks gleaming like captured moonlight. A simple furnace, brick-built and coal-fired, radiated steady heat beneath clay crucibles. On one bench rested brass candle holders adapted to hold glass jars. On another, a rudimentary bellows promised to stoke unexpected flames. In a corner stood his prized possession, an air pump of his own design, assembled with the help of Robert Hooke, whose mechanical ingenuity complemented Boyle's theoretical insight. The pump was the key to questions that had long plagued Boyle's mind. He suspected that air was not a passive void but a dynamic substance with weight and pressure. To test this, he needed a vacuum, a space devoid of air, and the ability to observe how creatures, flames, and sounds behaved in its presence. Hook's pump, with its leather valves and brass pistons, could evacuate air from a sealed glass vessel, leaving behind an almost perfect emptiness. On the day of the first experiment, Boyle stood before a small audience of curious scholars and students. Hook operated the pump with rhythmic precision, each turn of the handle drawing out more of the air. Inside the glass chamber, a flickering candle burned steadily at first, then sputtered, then extinguished as though the darkness itself had suffocated it. The audience gasped. Boyle noted every detail with meticulous care. Next came sound. A small bell hung inside the evacuated dome. When tapped from the outside, its ring grew faint as air vanished, until finally no chime could be heard. Silence enveloped the room, an eerie testament to air's invisible role in carrying sound. Boyle paused, letting the hush settle, then turned to his notebook and recorded his observations in precise language. Air supports flame and conveys sound, is no mere void but a substance of effect. These dramatic demonstrations were followed by gentler, more probing tests. Boyle placed a small mouse inside the vacuum chamber, its tiny chest moving in efforts that grew more desperate with each turn of the pump. Scholars expressed alarm, but Boyle insisted on scientific rigor. Let nature speak, however, quietly. At the moment of crisis, fresh air was reintroduced, and the creature revived, blinking in astonishment. The sight was both troubling and profound, proof of air's intimate connection to life itself. Word of these experiments spread quickly through Oxford's cloisters and beyond. The laboratory became a hub for visiting dignitaries, eager to witness the power and mystery of vacuums. Boyle, ever the gentleman, greeted each visitor with polite curiosity, always careful to let the data speak before offering his own conclusions. His notes grew into a manuscript detailing every experiment: numbers of pump strokes, durations of silence, measurements of flame height, charts of animal recovery. Yet no one was content with spectacle alone. Boyle sought deeper understanding. What was the nature of air that gave it these remarkable properties? How could such an invisible substance exert force, nourish flame, sustain life? He proposed that air consisted of countless particles in constant motion, pressing upon objects from every direction. To illustrate, he constructed a simple balance experiment. 2 identical chambers, one evacuated, one filled with air, each weighed on a brass scale. The scales tipped subtly, revealing that the chamber containing air was imperceptibly heavier. Though the difference was minute, it confirmed definitively that air possessed weight. Encouraged, Boyle expanded his investigations. He trapped air produced by various chemical reactions, by heating metals, by fermenting liquids, and compared their qualities. Some samples extinguished flame more quickly. Others burned it fiercely. One, collected from heated niter, intensified candlelight until the flame curled like a living thing. Boyle labeled these airs by their effects: vital air for the invigorating variety, mephitic air for the choking kind. He sketched diagrams of candle flames dancing under glass, of water bubbling with trapped gas, annotating each with careful precision. As the months passed, Boyle's laboratory became the epicenter of a new approach to natural philosophy. His insistence on quantifiable data and repeatable procedures marked a departure from the armchair speculations of earlier centuries. He corresponded with fellows in London and abroad, inviting them to replicate his work, to challenge his interpretations, to refine the methods. His manuscripts circulated among the informal network of experimenters that would soon coalesce into the Royal Society. The impact was profound. Air was no longer a mysterious element on par with earth or fire. It was a complex medium governed by mechanical laws. Boyle's Spring of the Air, as he described its elasticity and pressure, set the stage for precision studies of gases. His law, later to be enshrined as Boyle's law, emerged from these meticulous measurements, revealing the inverse relationship between pressure and volume. He showed that doubling the pressure on a trapped gas would have its volume, a fundamental principle with sweeping implications for physics, chemistry, and engineering. Yet for all the grandeur of his discoveries, Boyle remained ever the careful observer. He refined experiments again and again, acknowledging sources of error and refining equipment. If a reading did not match expectations, he examined every possibility: a leaky joint, an uncalibrated scale, a misread engraving on a barometer. His notebooks brimmed with corrections, marginal notes, and queries yet to be resolved, a testament to a mind that viewed science as an endless pursuit rather than a destination. By the time the Royal Society received its charter, Boyle's reputation was well established. His work exemplified the ethos of the new scientific community, progressed through collective verification, openness to challenge, and devotion to empirical evidence. The Society adopted his motto, Nullius in verba, take nobody's word for it, echoing Boyle's refusal to accept received wisdom without proof. In the years that followed, Boyle's experiments on air would inspire a generation of scientists. The vacuum pump, once a marvel in an Oxford laboratory, found its way into research centers across Europe. Engineers adapted his principles for diving bells and atmospheric engines. Physicians contemplated therapeutic uses of good air for maladies of the lungs. Boyle's clear, measured prose made his findings accessible, ensuring that the knowledge he generated would spread far beyond the cloisters of the university. And yet, in the quiet hours before dawn, long after the lab had closed and the pump stood silent, Boyle returned to his corner desk by candlelight. There, surrounded by sketches of glassware and stacks of correspondence, he pondered the mysteries that remained: the nature of heat in combination with air, the role of unseen particles in sound and light, the ultimate limits of experimentation. Each question he poised to tackle, each experiment he planned to refine, carried the spirit of that first day in Oxford, a spirit of humble inquiry ignited by a single conviction, that nothing about nature is too small or too invisible to escape the light of careful investigation. Boyle's law, unveiling the relationship of pressure and volume. Long before air was understood as the essential medium of life, Robert Boyle set out to measure its hidden properties with a precision never before attempted. In the spring of 1662, inside his Oxford laboratory, he embarked on experiments that would reveal a fundamental law of nature: that the volume of a gas varies inversely with the pressure exerted upon it. This insight, simple in statement, profound in consequence, would bear his name for centuries to come. Boyle's apparatus for these investigations was deceptively straightforward. He repurposed a tall glass tube, open at one end and sealed at the other, filled it with mercury, and then inverted it into a basin of the same liquid. The column of mercury trapped a sample of air at its sealed top, and the open end in the basin allowed Boyle to adjust the height of the liquid by adding or removing small weights, or by raising and lowering the tube itself. With each adjustment, he noted two measurements: the height of the mercury column and the corresponding clamped height of the trapped air above it. To ensure accuracy, Boyle designed his experiments to isolate as many variables as possible. The room's temperature was recorded before and after each trial, for he knew that heat could cause gas to expand or contract. He marked the tube with fine gradations, etched by hand, indicating precise increments of height. He employed a jeweler's balance to weigh any small attachments added to the apparatus, and he repeated each measurement several times to guard against stray errors. On the first morning, Boyle stood beside his apparatus as the early sunlight filtered through narrow windows, dust motes drifting through shafts of light. He added a small brass disc to the top of the tube, causing the mercury level to rise a fraction of an inch and compress the air beneath. He waited a moment for the system to settle, no sudden sloshing, no trapped bubbles rising, and then recorded the new height of the air column with meticulous hand. He repeated the process with successively heavier weights, watching the air volume shrink with each addition. In his journal he wrote in clear, deliberate script, "As the pressure upon the contained air increases, so does the contraction of its volume. A double load produces nearly half the space." This observation, rendered in the modest language of his time, encapsulated a truth far-reaching beyond the laboratory walls. Yet Boyle was not content with a single series of measurements. He and a young assistant, a diligent student from the college, spent weeks varying the experiment. They poured mercury at different temperatures, enclosed the apparatus in a draft-free alcove, and even tested different gases generated by early chemical reactions. Though pure air remained the primary subject, they observed that dense, vitiated airs behaved similarly, though with slight deviations beneath extreme pressures. Boyle was keenly aware of how revolutionary his findings might appear. In an era when many still believed air to be a mystical element, unquantifiable and bound to classical notions, here was a mathematical relationship, clear, reproducible, and grounded in observation. He drafted a memoir, writing for fellow natural philosophers. "I find that the height of the column of air is in reciprocal proportion to the weight of the load, provided the temperature remains constant." His phrasing, "reciprocal proportion," captured the inverse relationship. Increase one factor, decrease the other. When he presented these results to members of the Invisible College and the Young Royal Society, he did so with characteristic humility. Boyle demonstrated the apparatus himself, inviting skeptics to examine every joint and measure every height. He read aloud his data tables, row after row documenting pressure versus volume. Some listeners scratched their heads in quiet wonder. Others leaned forward, eyes alight with the prospect of practical application. It was a noble moment in the evolution of empirical science. The law that Boyle described would soon be quoted in treatises across Europe, inspiring further experiments on gas mixtures, heat effects, and the behaviors of different substances under pressure. Engineers designing pumps and diving bells began calculating the necessary resistance. Physicians speculated on the role of pressure in respiration. Philosophers saw in Boyle's law a model for uncovering hidden orders in nature. Back in his laboratory, Boyle continued to refine his understanding. He experimented with different cross-sectional tubes, ensuring that the shape of the container did not influence the results. He replaced mercury with water in small-scale trials to observe potential surface tension effects. He even theorized about the microscopic mechanisms, though atoms and molecules were not yet conceptualized, musing that countless tiny particles must press outward and be squeezed closer under added weight. His notebooks overflowed with marginal notes and sketches, little arrows indicating how one column of air rose as another sank, diagrams of shifting mercury levels, annotations on the roughness of the glass in certain sections. When a sudden chill seeped into the room one evening and cooled the mercury more quickly than the air, he observed a slight discrepancy. He noted it, shrugged, and scheduled further tests to compensate for temperature variations. Such attention to detail would make later generations bless his name for the rigor he applied. In the months that followed, Boyle published his law in the second volume of his collected works, sharing both the theoretical explanation and the practical details of his method. He included explicit instructions for building the apparatus, complete with suggested dimensions and cautions about impurities in the liquids. He argued that any natural philosopher could reproduce the experiment and verify the relationship for themselves. The importance of this openness cannot be overstated. By laying bare his procedures, Boyle invited collaboration and replication, breaking the tradition of guarded secrets that stifled progress in alchemy and earlier forms of natural philosophy. His law became one of the first truly universal principles of physics, applied to atmospheric studies, engineering pumps for mines, calculating safe depths for diving, and later to the design of steam engines in the following century. Beyond his immediate circle, news of Boyle's findings spread to universities in Leiden, Paris, and later, the American colonies. Scholars began to incorporate the inverse law into curricula, debating its implications for the nature of air and the broader behavior of gases. The term Boyle's law was coined in recognition of his pioneering work, and even as new laws, Charles's law, Gay-Lussac's law, emerged to describe relationships involving temperature, Boyle's original inverse proportionality remained foundational. Yet throughout his life, Boyle retained a sense of wonder at the simplicity and elegance of his discovery. He remarked in a later letter that he found it marvelous how such invisible substances as air should yield so readily to number and measure. He likened his experiments to unlocking a door to a hidden chamber of nature, one where each new observation revealed deeper layers of order. As scientific instruments grew more sophisticated in the centuries to come, the spirit of Boyle's law endured. High-pressure research, scuba diving, weather forecasting, even the study of respiratory physiology, all rested upon the principle that pressure and volume of a gas are bound in an unbreakable mathematical embrace. Modern devices, from anesthesia machines to rocket engines, trace their lineage to Boyle's humble glass tube and his patient recordings by candlelight. In the quiet of that Oxford laboratory, amid the hiss of mercury and the scratch of quill on parchment, Robert Boyle achieved something remarkable. He turned a mundane substance, air, into an object of mathematical beauty. He showed that nature's secrets yield not to proclamation but to careful measurement, that the invisible world obeys precise laws. And in doing so, he forged a path that countless seekers of knowledge would follow, ever deeper into the mysteries that surround us with every breath we take. Chemical transformation. Alchemy into chemistry. In the years following his celebrated experiments on air and vacuum, Robert Boyle turned his attention to a domain long shrouded in mysticism and secrecy: the art of alchemy. For centuries, alchemists had prized the transmutation of base metals into gold and the quest for the philosopher's stone above all else. Boyle, however, saw a different opportunity, an opportunity to transform alchemy's methods into the rigorous discipline of chemistry. He embarked on a personal mission to strip away the cryptic symbols and unverified claims of the alchemical tradition and replace them with clear procedures, reproducible results, and systematic inquiry. Boyle's laboratory became the crucible for this transformation. Where alchemists had once kept their recipes guarded behind locks and passwords inscribed in obscure ciphers, Boyle published his own protocols in meticulous detail. He described the precise quantities of reagents, the temperatures at which materials should be heated, the duration of each stage, and the visual cues, colors, precipitates, fumes that marked progress. By openly sharing every aspect of his work, he invited scrutiny, critique, and replication, creating a culture of transparency that was radically new. One of Boyle's early projects involved the study of acids and their reactions with metals. He prepared solutions of nitric acid by distilling saltpeter with vitriol and described, step by step, how to collect the concentrated liquid. He then tested its effect on various metals: copper, lead, iron, tin, observing the effervescence of gas, the formation of metal salts, and the colors of the resulting solutions. He noted that copper turned emerald green, lead produced a white powder, and iron yielded a pale yellow residue. Each result was recorded in his notebooks with sketches of crystal shapes viewed through a magnifying lens. These observations led Boyle to postulate that acids acted by combining with the metal atoms, creating new compounds that dissolved in water. He contrasted this behavior with substances that merely melted or sublimated under heat, demonstrating that chemical change, now called a reaction, could be distinguished from physical change. He coined the term corrosion to describe the slow action of acids on metals over time, and he proposed that the power of an acid might be measured by the rate at which it corroded a standard metal sample under controlled conditions. Boyle extended his studies to alkaline substances as well. He isolated potash from wood ashes by leaching and evaporation, then tested its ability to neutralize acids. He showed that treating a fixed amount of acid with increasing quantities of potash gradually reduced the effervescence and acidity, eventually yielding a stable salt. In one of his notebooks, he sketched a graduated series of glass jars, each containing equal acid but varying potash, and he recorded the precise point at which the mixture no longer bubbled. From these experiments emerged the earliest understanding of acid-base neutralization, and the concept that salts were the products of two mutually reactive substances. Not content to focus solely on liquids, Boyle also investigated the nature of gases produced by chemical reactions. He heated various metal carbonates, such as marble, a form of calcium carbonate, and trapped the gas evolved underwater, noting its volume and properties. He recognized that some gases, once freed from their parent compounds, exhibited behaviors distinct from common air. Certain gases extinguished flames, others supported more vigorous combustion, and some proved heavy enough to accumulate in low-lying cavities. These experiments complemented his earlier pneumatic studies and deepened the conceptual separation between air as a mixture and air as a reagent in chemical processes. Perhaps most significantly, Boyle challenged the prevailing theory of the four elements: earth, water, air, and fire, as described by Aristotle. He insisted that substances should not be categorized by mystical qualities but by their observable components and behaviors under controlled tests. In his seminal work The Skeptical Chemist, Boyle argued that what mattered was the identification of corpuscles, tiny particles of matter that combined in various ways to form the substances we observe. He proposed that elements were simply those corpuscles that could not be broken down further by known methods, thereby redefining the very meaning of element in chemical terms. The Skeptical Chemist was as much philosophical treatise as laboratory manual. Boyle scrutinized ancient authorities, pointing out the inconsistencies and contradictions in their classifications. He dissected chemical theories that relied on unverified assumptions, demanding that every claim be backed by experiment. The book circulated widely among scholars, sparking debate and encouraging a new generation of thinkers to adopt empirical methods. Boyle's influence extended beyond his own experiments. He mentored students, corresponded with fellow natural philosophers across Europe, and supplied glassware to colleagues eager to replicate his work. He took particular care to standardize the quality of reagents, urging that all preparations be described not by vague terms like strong spirit or soft water, but by precise sources and purification methods. This insistence on standardization laid the groundwork for reproducible chemistry, a principle that endures in laboratories around the world. Toward the end of his life, Boyle's interests broadened to include physiological chemistry, the study of the chemical processes underlying living organisms. Drawing on his earlier work with gases, he speculated on the role of vital air in respiration and proposed that the lungs acted as chemical filters, exchanging gases that nourished the body. Though the details of his theories would be refined by later scientists, Boyle's integration of chemical methods with questions of medicine and biology marked an important step toward interdisciplinary science. By the time of his death, Robert Boyle had transformed chemistry from a secretive art into a systematic science. His legacy lay not only in the discoveries he made, laws of gas behavior, methods of acid-base analysis, corpuscular philosophy, but also in the ethos he championed, that nature's hidden workings could be unveiled through careful observation, transparent reporting, and collaborative verification. The laboratory, once the domain of solitary alchemists, became a space of open inquiry. Chemical knowledge, once jealously guarded, became a shared resource. In the mid-17th century, Robert Boyle had not merely uncovered the mysteries of gases and reactions. He had redefined what it meant to pursue knowledge of the natural world. Boyle and the philosophy of nature. In the hushed corners of his Oxford laboratory, Robert Boyle often paused between experiments to ponder the deeper questions that lay beyond glass vessels and burning flames. More than a skilled experimentalist, he was a thoughtful philosopher of nature, convinced that the study of the material world could illuminate not only practical matters but also the grandest questions of creation, purpose, and human understanding. In this chapter of his life, Boyle wove together empirical rigor and reflective inquiry, forging a vision of science that embraced both meticulous measurement and profound wonder. Boyle's philosophical journey was shaped in part by his upbringing. The Earl of Cork's library at Lismore Castle had offered him an early education in theology, classical literature, and the esoteric arts of alchemy. Yet from these varied influences he emerged with two central convictions. First, that nature was the book of God to be read carefully and respectfully, and second, that human reason, when paired with diligent observation, could uncover truths hidden beneath the surface of appearances. These convictions found expression in his seminal treatise, The Skeptical Chymist, published in 1661. Far more than a critique of medieval alchemy, the work was a philosophical manifesto. Boyle challenged the age-old doctrine of the four elements: earth, water, air, fire, and the humoral theory of bodily fluids. He argued instead for a corpuscular philosophy, proposing that matter consisted of tiny particles whose arrangements and motions determined the properties of substances. In clear, persuasive prose, he insisted that genuine knowledge must rest on experiment, not on mere authority of classical texts. Boyle's writing brims with thoughtful asides and probing questions. He asks, for instance, how we can assert that a substance is elemental if we lack methods to decompose it further. He invites readers to imagine ever more refined apparatus, capable of subjecting materials to new pressures, temperatures, or chemical reagents, each test pushing the boundaries of what counts as indivisible. This open-endedness became a hallmark of Boyle's philosophy. Science, he believed, must remain inquisitive and humble, never resting on absolute claims but always inviting further scrutiny. Alongside his theoretical work, Boyle wrote extensively on the relationship between science and religion. He rejected any notion that natural philosophy might threaten faith. To Boyle, uncovering the mechanisms of nature was an act of devotion. Each law discovered, each reaction measured, testified to the orderly intelligence of the Creator. He cautioned against those who derided religious belief in the name of scientific progress, warning that wisdom without virtue could become hubris. In his view, integrity of character, humility, charity, honesty, was as essential to the scientific endeavor as precision of measurement. Boyle's letters to colleagues across Europe reveal the depth of his philosophical engagement. He corresponded with theologians and poets as well as with chemists and mathematicians, weaving a network of ideas that spanned disciplines. When the French scholar Pierre Gassendi sent Boyle a copy of his revival of Epicurean atomism, Boyle replied with respectful critique, acknowledging Gassendi's clarity of expression while questioning certain implications for divine providence. He strove consistently to balance openness to new models of matter with reverence for the moral and spiritual dimensions of existence. In 1674, Boyle delivered a series of lectures later published as Disquisition about the final causes of natural things. There he examined teleology, the idea that natural features serve specific purposes, and its place in natural philosophy. He critiqued those who saw every aspect of nature as designed solely for human benefit, urging instead a broader vision in which the cosmos operated according to laws imbued with beauty and harmony beyond human ends. He marveled at the intricate details of insect flight, the patterns of plant growth, the cycles of the stars, each phenomenon suggesting a cosmos rich with intention and elegance. Boyle's philosophical reflections also guided his approach to ethics in research. He insisted on transparency of methods and honesty in reporting results, condemning secretive alchemists who claimed cures or transmutations without divulging their processes. He maintained that falsified or incomplete accounts harmed the collective quest for truth and corrupted the very spirit of inquiry. In this, he anticipated modern codes of research integrity, emphasizing that the reliability of science depends on trust, collaboration, and the willingness to expose one's work to critical evaluation. Yet amid these lofty ideas, Boyle never lost sight of the wonder that first drew him to study nature. Late at night, after candles had guttered low and assistants had departed, he would linger by the window of his laboratory, tracing constellations in the vaulted sky. He saw the same patterns in microscopic crystals as in distant galaxies, the reflection of universal order at every scale. In this contemplative stillness, theory and practice converged, science and poetry entwined. In his final years, Boyle revisited questions of human physiology, drawing on his earlier experiments with vital air. He speculated on the role of respiration in sustaining life. He imagined the blood as a river of mixtures, the lungs as chemical laboratories exchanging substances in each breath. Though lacking the tools of later biomedical research, his corpuscular framework provided a conceptual basis for understanding bodily processes in chemical terms. He advised physicians to consider the composition of inhaled and exhaled air in treating lung ailments, a proposal that foreshadowed the development of respiratory therapy centuries later. As Boyle's health declined, he found comfort in reflection. He composed meditations on mortality, viewing death not as an end but as the completion of a life dedicated to understanding creation. He wrote of the hope that knowledge would live on in the minds of others, passed from teacher to student, from one generation of experimenters to the next. On his final day, surrounded by family and trusted friends, he expressed no fear, only gratitude that he had pursued truth in both laboratory and library. Robert Boyle's legacy as a philosopher of nature endures in the very structure of modern science. The integration of empirical methods with reflective questions about significance and purpose, the commitment to transparency, skepticism, and collaboration, and the recognition that the pursuit of knowledge is inseparable from reverence for the mystery and majesty of the world. In Boyle's thought, we find not only the foundations of chemistry but also a guiding light for the ethical, intellectual, and spiritual dimensions of scientific inquiry. Personal life and patronage. Though Robert Boyle's name is forever entwined with pioneering experiments and philosophical treatises, he was equally defined by his kindness, generosity, and deep sense of responsibility toward both science and society. In this chapter of his life, we explore the man behind the laboratory, the friend, mentor, and patron whose character shaped the course of his work and touched countless lives. Boyle never married, yet he spoke often of family, drawing affection and inspiration from those closest to him. His younger sister, Lady Catherine Jones, known to friends as Lady Ranelagh, shared his intellectual curiosity and provided steadfast support. When Boyle struggled with solitude or illness, it was to her letters he turned. She, in turn, found in his observations a source of lively discussion, encouraging him to pen accessible accounts of his experiments for a wider audience. Their correspondence, rich with mutual respect and warmth, offered Boyle solace and affirmation, reminding him that the pursuit of knowledge was most rewarding when shared. As Boyle's reputation grew, so did invitations to tutor and advise the children of noble families. He accepted positions with a select few, not for financial gain. He inherited considerable estates from his father, but out of genuine delight in guiding youthful minds. In a grand house along the Thames, he presided over small classes of eager students, blending rigorous instruction in Latin and mathematics with lively demonstrations of pneumatic engines and chemical curiosities. He spoke to them not as oracles but as companions in discovery, encouraging questions, nurturing wonder, and instilling in each pupil the conviction that truth emerged only through patient inquiry. His role as mentor extended beyond formal teaching. Boyle maintained an open-door policy at his London lodgings, welcoming visitors of all backgrounds, From ambitious young scholars to humble craftsmen with new mechanical designs, from physicians curious about his findings on vital air, to devout guests seeking counsel on reconciling science and faith. In these gatherings, he brewed herbal teas and offered small comforts: a warm hearth, a listening ear, a gentle word, bringing together minds as diverse as his own pursuits. Boyle's generosity manifested most tangibly in his patronage of fledgling scientific societies and charitable endeavors. He was among the earliest benefactors of the Royal Society, contributing not only his experiments and writings but also crucial financial support. When the Society's coffers ran low, Boyle quietly underwrote the printing of their philosophical transactions, ensuring that new discoveries reached scholars across Europe. He refused public accolades for these acts, insisting that his contributions served a higher purpose: the collective advancement of knowledge. Beyond the scientific community, Boyle directed resources toward the needy and the ill. A devout Christian, he believed that wealth was a stewardship entrusted by Providence to be used for the relief of suffering. In the harsh winters that afflicted London's poor, he organized distributions of warm clothes and dried foods, drawing on his network of colleagues to identify families in distress. He visited hospitals regularly, conversing with physicians and nurses about ailments, particularly of the lungs and throat, that might benefit from improved ventilation or fresh, good air. His suggestions led to modest but meaningful improvements in ward design, with larger windows and better drafts that eased patients' breathing and reduced the spread of disease. These charitable efforts were not acts of distant philanthropy, but expressions of Boyle's conviction that science must serve humanity. He once wrote, "What use is any knowledge if it cannot alleviate human misery?" His focus on air, its composition, pressure, and purity, stemmed not only from intellectual fascination but also from concern for miners working in foul shafts, sailors confined below decks, and the sick cradled in stuffy wards. Boyle envisioned a world in which understanding the properties of air would translate into fresher living spaces, safer deep-sea ventures, and therapies for consumptive maladies. Even in the 17th century, his ideals anticipated modern environmental health and respiratory medicine. Boyle's patronage also extended to the arts and letters. He recognized that scientific and cultural achievements flourished best in an atmosphere of creativity and dialogue. Through discreet endowments, he supported poetic contests and dramatic readings at local theaters, believing that the same imaginative spark driving a dramatist to shape a story could inspire a natural philosopher to conceive a bold experiment. He sponsored translations of classical works on Aristotle, Pliny, and Galen, accompanying them with critical footnotes that highlighted passages deserving fresh investigation or reinterpretation in light of empirical findings. At Christmastime, Boyle hosted gatherings that brought scholars, clergy, poets, and artisans under one roof. The great hall would shimmer with candlelight, the air thick with the scent of roasted meats, spices, and wood smoke. Guests dined on elaborate platters, but between courses Boyle would rise, his voice calm yet resonant, offering brief demonstrations. A sealed flask in which air had been pumped out so that a small bird hovered motionless, a retort in which metals shimmered under gentle heat, transforming before astonished eyes, a simple balance weighing the lightest of feathers against an equal weight of air itself. Such moments, blending artifice and insight, united the practical, the philosophical, and the poetic, showing that knowledge and beauty need not occupy separate worlds. In quieter seasons, Boyle withdrew to the countryside estates he inherited, a patchwork of farms and orchards, meadows and woodlands. There, amid the rhythms of planting and harvest, he found solace and inspiration. He walked winding lanes flanked by hawthorn hedges, pausing to sketch wildflowers, record the calls of birds, and hose down brass instruments for his experiments. In one gently sloping orchard, he erected a small pavilion filled with his most delicate glassware, where he studied dew formation at dawn and the way sunlight fractured through water droplets on leaves. Though removed from academic centers, He remained in close contact with colleagues, dispatching letters that carried wood samples, botanical sketches, and queries about atmospheric moisture. It was in these pastoral retreats that Boyle met a variety of European travelers: landscape painters seeking the vivid greens of English countryside, botanists eager to catalogue unique specimens, noblewomen interested in the medicinal herbs growing wild at their feet. He guided them through orchards heavy with fruit, demonstrating how essential oils could be extracted by simple distillation, how plant-based vinegar might preserve berries for winter sustenance, and how apple spirits, later distilled as brandy, could be used for digestive relief. These demonstrations blurred the boundary between gentleman scholar and practical innovator, showcasing science as a hands-on craft woven into everyday life. Boyle also extended his patronage to international scholars facing hardship. When religious or political turmoil forced scientists on the continent into exile, he offered them temporary lodging and stipends, recognizing that the pursuit of knowledge was a universal vocation transcending national borders. Spanish and Italian chemists, French astronomers, and even occasional Polish alchemists found refuge in his London lodgings, their presence enriching Boyle's own perspectives and weaving new threads into the tapestry of emerging science. One poignant episode involved the philosopher John Locke, whose political misfortunes had led him to England. A chance meeting between Boyle and Locke blossomed into a deep friendship grounded in mutual respect for reason and conscience. Boyle supported Locke's work on human understanding, providing access to his extensive library and encouraging Locke's inquiries into the nature of perception, identity, and the limits of human knowledge. Their conversations, extending through candlelit nights, fostered early ideas that would later shape modern empiricism and political philosophy. Despite his busy schedule of experiments, teaching, and patronage, Boyle remained attentive to his own health and well-being. He adhered to a regimen he believed balanced body and mind: moderate exercise in the form of daily walks, a simple diet of fresh and preserved foods, and regular periods of rest. He kept meticulous notes on his physical condition, paradoxically applying the same empirical approach to personal health that he used in his laboratory. These practices sustained his vigor well into his 70s, a remarkable feat in an age marked by shorter lifespans. As Boyle entered his later years, his style of laboratory work gradually shifted. He delegated routine procedures to younger assistants, focusing instead on conceptual synthesis and the patronage of promising students. His laboratory staff became a community of mentored pupils, some from noble families, others from modest backgrounds, united by devotion to inquiry. Under Boyle's guidance, they learned to design experiments, maintain precise records, and write clear reports. His gentle yet firm mentorship instilled in them a dedication to ethical research, transparency of methods, and openness to critique, values that would define the emerging scientific profession. Boyle's generosity of spirit extended to the careful stewardship of his own legacy. He took steps to catalogue his extensive library, ensuring that manuscripts on gas experiments, notebooks of chemical reactions, and philosophical essays were preserved for posterity. He provided funds for binding and indexing these volumes, and he bequeathed his collections to institutions prepared to safeguard and disseminate them. His vision was not to remain a solitary repository of knowledge, but to lay the foundations for ongoing discovery. In his final decade, Boyle faced periods of ill health that forced him to slow his pace. Yet even then, his concern for others never waned. He continued to write to colleagues, offering counsel on scientific and moral matters alike. When plague struck nearby counties, he dispatched care packages of medicines and urged those with means to support local relief efforts. He wrote poems of consolation for friends who had lost loved ones, pairing his scientific acumen with heartfelt compassion. On a mild spring day in 1691, surrounded by close friends, family, and a handful of devoted students, Robert Boyle passed peacefully from this life. His last words, according to one loyal assistant, were an exhortation to let every man be as much as in him lies a good friend to mankind. His funeral drew scholars from across England and abroad, a testament to the far-reaching impact of both his scientific contributions and his charitable spirit. Robert Boyle's personal life and patronage remind us that the greatest breakthroughs in understanding arise not only from clever experiments, but also from a generous heart in a committed community. He transformed chemistry through glass and flame, yes, but equally, he transformed the practice of science into a collaborative, ethical, and humane endeavor. The laboratories and societies he supported, the students he mentored, the charitable causes he funded, all these stand as living monuments to the man who believed that knowledge and compassion walk hand in hand. In Boyle's world, the pursuit of truth and the service of humanity were inseparable callings, each enriching the other in a harmonious dance that continues to inspire seekers of wisdom today. Late years and enduring legacy. As Robert Boyle entered his 7th decade, the steady rhythm of his scientific work gave way to deeper reflections on the meaning of a life devoted to unraveling nature's secrets. No longer driven by the urgency of youthful discovery, he turned his gaze toward consolidating his achievements and ensuring that the principles he had championed would guide future generations. In these later years, his laboratory slowed to a gentle hum. His correspondence took on a philosophical cast, and his legacy, already remarkable, would solidify into a foundation upon which modern science would stand. Born in 1627, Boyle had long since outlived many of his contemporaries. The turmoil of the English Civil War, the Restoration, and the Great Plague had faded into memory, but the lessons learned in those turbulent times shaped his convictions. That knowledge must be earned through diligent effort, not inherited by birthright. That open discourse and mutual critique are the lifeblood of progress, and that science, properly practiced, serves the welfare of all humankind. By the 1680s, Boyle's health had begun to wane. Periodic bouts of gout confined him more frequently to a chair or to his countryside lodgings than to the laboratory bench. Yet even as physical vigor declined, his intellectual energy burned brightly. He continued to receive young scholars and visiting dignitaries, offering advice on experimental design, moral counsel, and logistical support for fledgling research societies abroad. His home in Pall Mall became a sanctuary where science and faith coexisted in respectful dialogue, where theological questions, about the compatibility of mechanistic explanations with divine purpose, were pursued with the same rigor as chemical assays. Unable to perform long, strenuous experiments himself, Boyle shifted his focus toward collaboration and mentorship. He gathered around him a circle of devoted assistants, some of them sons of noble families, others young men of modest means drawn by his reputation. These pupils carried out the intricate tasks of heating retorts, weighing minute samples of salts, and charting the behavior of gases under novel conditions. Boyle guided them through each procedure, reading their draft manuscripts, suggesting improvements, and emphasizing the importance of recording every variable: temperature, humidity, purity of reagents, atmospheric pressure. Through this process, he instilled his own standards of experimental integrity, ensuring that his methods would be replicated faithfully and extended innovatively. One of the most significant threads in Boyle's late work was his ongoing interest in the chemical basis of health and disease. Building on his early studies of vital air, he speculated about the role of specific gases in physiological processes. In correspondence with physician friends, he proposed that animals, and by extension humans, might thrive or suffer depending on the proportions of good and corrupt airs inhaled. He advocated for better ventilation in hospitals and prisons, suggesting that stale, noxious air contributed to outbreaks of consumption and fever. Though he lacked modern instruments to quantify oxygen levels or microbial contamination, his empirical observations, linking overcrowded wards with higher mortality, improved outcomes in airy chambers, foreshadowed the development of public health measures and environmental medicine. In pursuit of these ideas, Boyle supported early experiments on breathing apparatus. He provided funding and technical guidance to inventors attempting to create devices for underwater exploration or for assisting miners in dangerous shafts. While these mechanical prototypes were rudimentary, leather bellows pumping air through tubes, pig bladders used as crude reservoirs, they marked a critical shift. The notion that engineered systems could augment and protect human life by manipulating the very gas essential to our existence. Amid these scientific endeavors, Boyle remained a devout churchman, serving as an elder in the Church of Ireland's Convocation when political circumstances allowed. Although he had spent much of his life in England, his Irish roots and early education imbued him with a lifelong concern for the spiritual as well as the material well-being of his countrymen. He contributed generously to the construction and repair of parish churches, often stipulating that part of the endowment include funds for poor relief and education. In his will, he directed that a portion of his estate support scholarships for students of both theology and natural philosophy, believing that each field enriched the other. Boyle's writings during this period also turned inward, reflective, and occasionally lyrical. He compiled meditations on the art of experiment as a spiritual discipline, the patience required to observe subtle changes, the humility to accept unexpected outcomes, the charity to share knowledge without pride. He reconceived the laboratory as a temple of inquiry, where each measurement was an act of worship, each discovery a revelation of divine wisdom. These essays, less technical than his earlier treatises, circulated among his friends in manuscript form, offering guidance not only to practitioners of science but to any earnest seeker of truth. As a man of means, Boyle had long eschewed financial gain from his writings and patents. In these later years, he devoted himself to ensuring that his personal fortune served the public good. He established charitable trusts to support widows of clergy, to fund apprenticeships for young artisans, and to supply medicine chests to rural parishes. He sponsored voyages of exploration, equipping ships with chemicals for testing water salinity and sampling new plant species. In one remarkable instance, he funded an expedition to the Caribbean explicitly to study the effects of tropical climates on the decomposition of organic matter, an early foray into the field of tropical ecology. Boyle's commitment to open science was perhaps most evident in his final years through his patronage of scholarly publication. Recognizing that high-quality printing was essential to disseminating accurate knowledge, he negotiated with London presses to standardize typographic conventions for scientific works, uniform tables of contents, consistent footnoting of apparatus dimensions, and precise indexing of experimental data. He contributed funds to produce affordable editions of his major treatises in multiple languages, English, Latin, French, so that language barriers would not impede the spread of reliable methods. By the early 1690s, signs of age had begun to weave silver threads through Boyle's hair, and lines traced the year's labors upon his face. Yet his eyes retained a lively spark. He continued to attend meetings of the Royal Society when able, listening attentively to presentations on new telescopic discoveries, anatomical observations in distant lands, and mathematical models of lunar motion. He rarely spoke at length, but when he did, his remarks carried the weight of authority tempered by a lifelong readiness to learn. Younger fellows regarded him with veneration, not as an untouchable legend but as a generous mentor whose door, and whose mind, remained open. In one of his final public acts, Boyle addressed the Society on the importance of encouraging women in natural philosophy. Though his own circle included few women in the laboratory, he recognized their intellectual capacity and urged that future generations not deny gifted minds the opportunity to contribute. This statement, radical for its time, reflected Boyle's broader commitment to inclusivity in the pursuit of knowledge. On December 31, 1691, Robert Boyle's body finally succumbed to the cumulative toll of decades spent in service to science and humanity. He died peacefully in his London home, surrounded by friends, family, and faithful students who had gathered to pay their last respects. His final written words found beside his quill reflected his enduring priorities. I commend to posterity the practice of experiment, the care for the poor, and the undying search for truth, wherever it may lead. Boyle's funeral was a solemn and dignified affair. Scholars and clergy processed through Pall Mall to the Church of St. Mary Aldermanbury, carrying his manuscripts, laboratory sketches, and personal effects. Eulogies celebrated not only the first great chemist of our age, but also the kind patron, the devout friend, the humble servant of knowledge and of God. His remains were interred in the vaults of Westminster Abbey, placing him among England's most revered figures of letters and science. In the years that followed, Boyle's legacy grew in both scope and depth. His law became a cornerstone of physical chemistry, his methods foundational to laboratory practice, and his philosophical writings a touchstone for debates on the relationship between science and religion. Institutions bearing his name, Boyle lectures, Boyle studies at universities, endowed chairs, ensured that each generation would encounter his example. But perhaps his most enduring legacy lies less in eponymous laws or endowed professorships than in the spirit he embodied, a spirit of open inquiry, ethical responsibility, and compassionate service. Robert Boyle's life demonstrated that the quest to understand nature is inseparable from the duty to improve human welfare, and that patience, humility, and generosity are as essential to the advancement of knowledge as curiosity, creativity, and technical skill. Today, as scientists probe ever deeper into the molecular and cosmic realms, they stand on the shoulders of Boyle's insights and on the foundation of the practices he established. Yet the true measure of his impact may be heard in the simple turn of phrase often repeated among researchers: take nobody's word for it. In those 8 words, Boyle distilled his credo, a lifelong conviction that truth emerges only through evidence, collaboration, and an unwavering commitment to the betterment of humanity. And in that commitment, his legacy continues to breathe life into the ever-evolving world of science. Legacy and the gentle descent into rest. Robert Boyle's life unfolded at the nexus of experiment and reflection, of discovery and devotion. In his later years, as the flame of youth dimmed into a steady glow, he turned his thoughts not only to what remained to be learned but also to what must be preserved. What lessons, what values, what sense of wonder the next generation should inherit. Over decades, countless experiments had revealed the hidden workings of air, acids, and the tiny particles he called corpuscles. He had charted mathematical laws, dismantled alchemical dogma, and argued for a philosophy rooted in evidence. Now, as he prepared for the final chapter of his own life, Boyle contemplated the legacy he would leave behind. A legacy of method, of humility, and of the conviction that knowledge and compassion are inseparable. In the autumn of 1688, Boyle felt his strength begin to ebb. Nights grew restless. Gout seized his limbs. Yet even as his body demanded rest, his mind refused to quiet. He spent long evenings at the window of his London lodgings, gazing out at the moonlit rooftops, pondering the many ways vital air sustained not just flame and living creatures but also the very spark of inquiry that animated human hearts. He wrote letters recommending improvements in ventilation for hospitals. He drafted guidelines for preserving manuscripts. He revised lists of beneficiaries for his charitable trusts, ensuring that poor scholars would continue to receive support, that widows of clergy would find succor, that scholars on the continent fleeing turmoil would find refuge and resources. Boyle's correspondence from this period reveals a poignant blend of concern for the future and a serene acceptance of his own mortality. He instructed his assistants to organize his laboratory notes in carefully bound volumes, each indexed and cross-referenced. He arranged for duplicates of precious manuscripts to be sent to university libraries in Oxford and Dublin, safeguarding against loss by fire or war. When a fire broke out in a neighboring street, he dispatched servants to rescue glassware and diaries, crying out for the lamp that held the original data from his first piston and pump experiments. "Better the vessel burn than the record vanish," he scribbled in the margin of a letter. Amid these practical concerns, Boyle's thoughts turned again to the philosophical roots of his work. He composed meditations on the art of experiment, likening the patient observer to a humble pilgrim seeking illumination. He argued that every failed trial, every unexpected result, was a gift, an invitation to question assumptions and refine methods. He urged young scientists to cultivate not only dexterity with retorts and balances but also patience, modesty, and a spirit of generosity. In his view, science without character risked devolving into mere trickery. Knowledge divorced from compassion could become cold and destructive. One crisp December morning, Boyle convened his final gathering of household assistants and close friends in his study. The great table, worn by decades of candlelit debates and careful weighing of salts, served as both altar and workshop. Boyle opened with a soft prayer of thanks, an acknowledgement of the Creator whose laws he had sought to uncover. He then shared a simple meal of pottage and fresh bread, passing around small flasks of distilled waters and smelling salts he had prepared to ease winter colds. Conversation ranged from the latest celestial observations to the progress of a young chemist in Leiden experimenting with phosphorus. Boyle listened with bright eyes, occasionally interjecting a question or kindly correction, always mindful that even the humblest voice might spark a fresh insight. That afternoon he delivered an informal lecture, his last, to a small circle of pupils. He recounted the story of his first vacuum pump experiment, describing the gasp in the audience as the candle flickered out and the bell fell silent. He spoke of the thrill of plotting pressure and volume on a humble glass tube, of witnessing the birth of what would become Boyle's law. He reminded them that no matter how great a discovery might seem, it remained but one step on an endless path. "Let curiosity be your compass, and let kindness light your way," he concluded, his voice firm despite the tremor that sometimes betrayed his age. As dusk fell, the pupils bid him farewell, promising to carry forward his methods and uphold his values. Boyle watched them depart, then closed the shutters against the night and retreated to his bedside. His final notebooks lay on a small table nearby, blank pages awaiting new observations he would never record. He paused, touching the smooth leather binding, and whispered a silent vow that this empty space would one day be filled by the work of others. Over the following weeks, Boyle's health fluctuated. Some days he sat at his desk, sketching small diagrams of crystal formations or jotting clarifications to earlier essays. On others, he lay by the hearth, reading comforting passages from scripture and the works of ancient philosophers. He engaged in long conversations with his physician about the nature of remedies: wine distilled with lavender, linen bandages smeared with balsam, and speculated on the chemical actions at play even in these simple treatments. Though the world grew dimmer around him, the world within his mind remained vivid with questions and quiet discoveries. On a clear January night, Boyle made a final entry in his private journal. He wrote of the invisible kindness of air, suffused with the breath of life and the promise of revelation. He described how each inhalation connected him to the cosmos, an unbroken thread linking his small lungs to distant stars. He noted how, as he exhaled, he gave back to that same cosmos the spent air of a grateful soul. He ended with a line of gentle resolve: "Let my last breath be a benediction to those who follow." Within days, Boyle's strength waned beyond the need for further experiments or discourse. Friends and servants gathered, drawn by loyalty, admiration, and affection. He received them one by one, offering soft words of encouragement: pursue truth without fear, serve humanity without hesitation, treasure each mistake as well as each triumph. To one dear friend, he entrusted a bundle of letters to publish posthumously. To another, he left instructions on the proper disposal of chemical waste, an early expression of environmental consciousness. On the morning of March 31, 1691, Robert Boyle drew one last breath beneath the pale light of a spring dawn. His passing was peaceful, his face composed, as though he had slipped into a gentle slumber. Those present felt the hush of loss meet the hush of wonder, an echo of the very silences he had explored in his vacuum chambers. No pomp or ceremony awaited him, only the sincere mourning of those who understood that a life invested in kindness, rigor, and unending curiosity can never truly end but lives on in every mind it inspired. Boyle's will stipulated a simple funeral and the distribution of his remaining wealth to the causes he cherished: scholarships for aspiring natural philosophers, relief for impoverished families in Ireland, and support for the Royal Society's publications. His personal effects, laboratory instruments, notes, manuscripts, were entrusted to trusted colleagues, with a request that they preserve and share his work rather than hoard it. True to his ethos, Boyle asked that no mausoleum be erected in his honor, only a modest gravestone bearing the words, "Here lies Robert Boyle, friend of mankind." In the years that followed, Boyle's influence only grew. His law of gases became fundamental to physics. His approach to experimentation shaped the structure of laboratories worldwide. His corpuscular philosophy paved the way for atomic theory. Generations of scholars read and reprinted his works, debated his ideas, and extended his methods to realms he never imagined: electricity, microbiology, quantum mechanics. Through wars and revolutions, through shifting political and religious tides, the principles he championed endured: reproducibility, transparency, humility, and compassion. At Oxford and Dublin, Boyle's name graced lecture halls and statutes. In London, his portrait hung among scientists who followed in his footsteps. Yet perhaps his greatest monument was invisible: the countless lives eased by cleaner air in hospitals, the curious children ignited by stories of his experiments, the ethical standards upheld by researchers who took nobody's word for it as their guiding creed. These living legacies, woven into the fabric of science and society, are the echo of Boyle's final request: that knowledge be shared, that inquiry be fearless, and that every breath we take reminds us of the wonder and responsibility of being alive. And in the quiet moments before sleep, when the mind drifts through the corridors of memory and imagination, we may yet hear a soft whisper carried on the breath itself: "Seek truth, serve others, and let your curiosity light the way." In those words, Robert Boyle continues to breathe life into every heart willing to question, to learn, and to care. The ripple effect: Boyle's enduring impact on science. Long after Robert Boyle's own candle burned out in that final Oxford night, the principles he established continued to illuminate countless paths of inquiry. His meticulous experiments, his insistence on transparent methods, and his corpuscular philosophy left indelible marks on the emerging fields of chemistry, physics, physiology, and engineering. In this chapter, we trace the wide-reaching influence of Boyle's work, from the laboratories of the Enlightenment through the Industrial Age and into the modern era. 1. Foundations of modern chemistry. Boyle's rejection of alchemical secrecy and his call for reproducible procedures laid the groundwork for chemistry as a systematic science. In The Skeptical Chemist, he proposed that elements be defined not by tradition or mystical properties but by their inability to decompose under known operations. This empirical criterion directly influenced later scientists such as Antoine Lavoisier, who built upon Boyle's corpuscular framework to establish the law of conservation of mass and to construct the first modern list of chemical elements. Boyle's acid-base studies prefigured titration techniques. His isolation and classification of airs anticipated the discovery of gases like oxygen, hydrogen, and nitrogen. By the early 19th century, the language and logic pervading chemical textbooks, terms like reaction, compound, and element, were inheritances of Boyle's insistence on clear definitions and precise measurements. 2. Birth of gas laws and thermodynamics. Boyle's quantitative law relating pressure and volume of a fixed quantity of gas became the first pillar in a family of gas laws. Charles's law, volume temperature, Gay-Lussac's law, pressure temperature, and Avogadro's hypothesis, volume molar quantity, all found a conceptual anchor in Boyle's original experiment. Collectively, these relationships form the ideal gas law, PV equals nRT, a cornerstone of thermodynamics. Engineers and physicists harnessed these ideas to develop steam engines, to design compressors and internal combustion engines, and to understand atmospheric phenomena. Boyle's early pump experiments foreshadowed the pressurized systems that power submarines and spacecraft, where controlling gas pressure and volume is a matter of survival. 3. Advances in physics and the mechanical philosophy. Boyle's air pump demonstrations underscored the importance of the experimental method in physics. His work influenced contemporaries such as Christian Huygens and Isaac Newton, who adopted similar rigor when probing optics, motion, and gravity. The philosophical shift that Boyle championed, viewing nature as governed by mechanical laws rather than mystical sympathies, paved the way for the mechanistic worldview of classical physics. In lectures and papers, Boyle's ideas supported Newton's derivation of universal gravitation and influenced the nascent field of hydrodynamics, where pressure-driven flows of fluids mirrored Boyle's observations of air under pressure. 4. Foundations of respiratory and environmental medicine. Boyle's early recognition that different airs affected living organisms inspired generations of physiologists and physicians. In the 18th century, Joseph Priestley and Antoine Lavoisier expanded on Boyle's work to identify oxygen's role in respiration and combustion. Subsequent research by pulmonologists and environmental health scientists traced respiratory diseases to air quality, building on Boyle's recommendation for improved ventilation in hospitals and mines. Today's fields of pulmonary medicine, anesthesiology, and hyperbaric therapy echo Boyle's emphasis on the therapeutic and harmful effects of gas mixtures on the human body. 5. Emergence of analytical techniques. By quantifying gas volumes, pressures, and reaction yields, Boyle set a precedent for analytical precision. Centuries later, techniques such as gas chromatography, mass spectrometry, and volumetric titration embody the same spirit of measurement and reproducibility. Analytical chemists isolate, identify, and quantify substances in complex mixtures with instruments that trace conceptual lineage to Boyle's burettes and balances. Quality control in pharmaceuticals, environmental monitoring, and food safety relies on these standards of accuracy he first advocated. 6. Institutionalization of science and peer review. Boyle's role as a founding member of the Royal Society, and his motto Nullius in verba, take nobody's word for it, anticipated the modern model of scientific publishing and peer review. Philosophical Transactions, the Society's journal first printed under Boyle's patronage, became the world's earliest continuous scientific periodical. Its format, method sections, data tables, cited references, set the template for scholarly articles. Today's global network of journals, editorial boards, and peer reviewers uphold Boyle's conviction that no claim should stand without public evidence. 7. Educational reform and public engagement. Boyle's clear writing and demonstrations rendered complex phenomena accessible to wider audiences. He inspired an era of popular science lectures, public experiments, and instructional manuals. In the 18th and 19th centuries, mechanical demonstrations of vacuums and pneumatic pumps drew crowds at scientific soirees and public fairs. Boyle's blend of spectacle and substance presaged modern science communication. Museums, planetariums, and science festivals continue to echo his approach of engaging the public through inquiry and wonder. 8. Ethical standards and open science. Boyle's moral imperatives, transparency of method, honest reporting, sharing of resources, set early examples for research ethics. His charitable distribution of equipment and reagents remains a model for capacity building in underserved regions. In contemporary movements advocating open access, data sharing, and collaborative platforms, Boyle's spirit is resurrected in calls to make scientific knowledge a global public good. 9. Inspiration for interdisciplinary inquiry. The breadth of Boyle's interests, from gas behavior to physiological effects, from experimental mechanics to theological reflection, demonstrated the power of interdisciplinary thinking. His life encourages modern scholars to cross boundaries between physics, chemistry, biology, medicine, and philosophy. Fields such as biophysical chemistry, environmental science, and chemical engineering flourish on the foundations of integration he exemplified. 10. The living legacy. Robert Boyle's name graces awards, lecture series, laboratories, and university chairs around the world, but his true legacy lives in the methods and mindsets he fostered. Every time a scientist designs a controlled experiment, meticulously records data, subjects conclusions to peer critique, or champions the ethical application of knowledge for human welfare, they echo Boyle's foundational insights. His life reminds us that science, at its best, combines precision with humility, curiosity with compassion. In tracing these ripples, from the first vacuum pump in a quiet Oxford workshop to today's high-tech laboratories and hospital wards, we see how one man's devotion to empirical inquiry has shaped centuries of progress. Boyle did more than measure gases. He breathed life into a new way of understanding nature, one built on evidence, reasoning, and an unwavering belief that knowledge, when pursued with integrity, enriches all of humanity. As we continue to explore ever deeper mysteries of atoms, cells, planets, and beyond, we carry forward his legacy in every careful measurement and in every question asked with both wonder and rigor. And so our journey alongside Robert Boyle comes to its gentle close. We have walked through candlelit chambers and bustling salons, peered into vacuums and watched flames dance under glass. We have traced the shifting levels of mercury, inhaled the whisper of vital air, and witnessed the birth of a method that would guide generations of seekers toward truth. Now, allow the excitement of discovery to drift away like vapor. Feel your shoulders soften, your jaw unclench, and each breath deepen. Imagine the soft glow of candlelight fading into the hush of evening, as the world settles into quiet rest. There is nothing left to do but let go of thought and follow the natural rhythm of inhalation and exhalation. With each exhale, release the cares of the day. With each inhale, welcome calm and serenity. Picture the Oxford rooftops under a starlit sky, the hushed corridors of ancient colleges, and the silent laboratory where glass vessels stand in patient watch. Let those images fade into the darkness behind your closed eyelids. Tonight, you too may rest in the company of wonder. Let the legacy of curiosity and compassion fill your dreams, carrying you into a peaceful slumber. Good night, and may your sleep be as deep and gentle as the truths we have uncovered together.